Okay, everybody got the worksheet, put your names on it. First thing we're going to do is we're going to do a word ball activity. So these are the vocab that we've already went over. Most of them are reviews, some of them are new. So I grouped them into categories that correspond with each other. So what I'm going to do is I'm going to call on y'all and tell me how they correspond, or tell me certain things about that vocab word. So first off, we're going to talk about bonding. Quentin, which is the strongest bond we've talked about? Yes, covalent. Why? What are the electrons doing? In covalent, you're a co-captain, you're shared, good. Which is the next strongest, but is pretty weak? Ionic, because you're an ion, you're doing what with the electrons? You're stealing, or you're taking it, good. So in covalent and ionic, there's electron exchange. What is the weakest? And it's just an attraction between two molecules and their polarity and their charge.
Hydrogen.
Hydrogen bonding, good. Next one, reactant, product, catalyst. If I'm baking a cake, what are my reactants? Ingredients, good, such as eggs, sugar, flour, water, good. What is the end product?
A cake.
A cake, good. What is the definition of a catalyst again? Come on, Cal, hurry up!
Oh, round them up.
Speed up. Speed up the reaction. You'll never forget it.
She said cattle.
What reactants could speed up the reaction of this cake?
Yeast.
Eggs. Yeast or eggs, good. So it'll make it rise more. So the reactants are all the ingredients, the end products to cake. Something that'll speed it up would be like the eggs or the yeast. Good. Okay, pH, acid, and base. So we have a scale from 1 to 14, or 0 to 14. The 0 side are what? Acids or bases?
Bases.
Someone said base. How are we supposed to remember it?
Never mind.
0 to
14 is base.
Good. So it goes A to B, 0 to 14. Okay? 7 is neutral. A to B, 0 to 14. 7 to 0 is acidic. 7 to 14 is basic. Is my milk with a pH 10 acidic or basic?
Basic.
Basic. Is my orange juice with a pH of 3? Perfect. Okay, now the big group. Neutron, compound, ion, atom, electron, proton, nucleus, isotope. Let's talk about the nucleus. What's in the nucleus?
Protons.
Good. What is the overall charge of the nucleus? Positive. Good, because a positive group and a neutral group equals overall positive. What are on the outside? Electrons. Good. If an electron is stolen, or that atom gains an electron, it becomes an ion. You're on. Remember, you've gotten something or you've given something. Isotope, you gain or lose neutron. Good. So iso meaning same. So if you gain a neutron, you still have the same atomic number. You have a different atomic mass, but you still have the same atomic number. Ion, when you're charged, that's when you actually gain an electron, okay? And your charge is different. Okay, the new words for today are diffusion, osmosis, and equilibrium. We watched that United Streamings video yesterday, so we got a good introduction to what it is, but today we're going to take notes on it and we're actually going to do a lot of the experiments. Okay, so the end goal for diffusion and osmosis is to get everything equal. We always want to maintain homeostasis. We always want the same on the inside as the same on the outside, okay? Or we always want the same concentration throughout. You can either move particles through diffusion or move water to get that equilibrium in osmosis. Okay, so let's start off on our notes. The first part is review. We went through a lot of this right up here. Water is one of the most important compounds. What is a compound? So you have individual atoms and then you have compounds.
They're made
Together group.
two different likes.
Two or more.
Opposites.
Two or more atoms together.
Yes.
Good. So compounds.
Blitzneck.
You have two or more atoms of an element bonded. So two or more atoms of an element bonded. Now, we already said water has a very strong bond. What kind of bond is water? Covalent, good. So how's it bonded? Water is bonded covalently. And covalent is super strong, okay? Now one thing I didn't put up on the word wall was the word polarity. What is polarity?
It's got a positive and negative side.
Good. It's when there's a positive side and a negative side. So you have opposite charges. And why is water polar?
Because it has
it has a positive side toward the hydrogens, that negative side toward the oxygens. Remember, oxygen's a really big atom compared to hydrogens. It's like the bully, and it wants to fill its outermost energy levels to become stable. So it really pulls on those atoms or those electrons from hydrogen. Okay, it gains a little of that negativity, so it becomes the negative part of that polar water molecule. Good. Polarity is when you have a positive side and a negative side.
Oh,
So it's when you have some charge.
just like those hormones, right?
And then water's polar because it does have that negative side with the oxygen and the positive with the hydrogen. Okay, so because my Promethean board isn't working that great, I did this next example in paint, so bear with me. But when molecules are polar or charged, do they get attracted to opposite charges or do you get attracted to the same charge? So if I'm water and I have a positive side and a negative side, is my positive side going to be attracted to another positive or to a negative? Positive to the negative, good. So when molecules are polar or charged, they're attracted to the opposite charge. That's how we hydrogen bond. And so below we're going to draw water and show its polarity and its bonds. So I'm going to bring up this paint diagram and I drew 3 water molecules. So remember 3 Mickey Mouse heads. You got the big oxygen and then the 2 hydrogens covalently bonded. And so what is that bond between the oxygen and the hydrogens?
We have to draw through that.
Yes, covalent. And what is the weakest bond between the water molecules? Where they don't share any electrons, they just have an affinity or a liking for each other. They're not sharing electrons.
They're breaking down.
So hydrogen bonding, good. Okay, so right now you're just going to draw the 3 water molecules and I'll show you where the bonds occur. So we established that within the water, the oxygen and hydrogens are covalently bonded. The water to water, what is water to water bonding? What kind of adhesion is it? Water to water, same molecule to same molecule? What kind of adhesion?
Cohesion.
Cohesion. If it was water to something else, it would be adhesion. Okay.
I spelled adhesion.
H-E-S-I-O-N.
Shit.
You know, my worst subject is English. Okay, so first thing I'm going to do is, to make this easier on me and you, is I'm going to draw the positive end and the negative ends of water. So then we can easily visualize where these bonds are going to occur. So where is the negative end of water?
The oxygen.
Good. So we got slightly negative, we got slightly positive. We got the positive and the slightly negative. We got the negative, slightly positive. So where do the bonds want to occur between charges that are similar or different? Opposite or different?
Different.
Opposite. Good. So the hydrogen bonds are going to want to occur between the negative oxygen end and the positive hydrogen end of another one. And so this positive end, or let's say this negative end, is going to be attracted to this positive here. This negative is going to be attracted to this positive end here. This positive end is going to be attracted to a negative oxygen end over here. So what I want you to do is put the charges next to the atoms, and then draw the hydrogen bonds. Good. Between the positive end and the negative.
So the very word.
And so hydrogen bonding was what kind of, was it a strong or a weak?
Right there.
Yep, that's perfect. Strong or weak? Hydrogen bonding, strong or weak?
Weak.
Weak, because we're not even sharing electrons. We're not taking electrons, but there is still an affinity. So it is kind of easy to break these bonds. What I ask you right here is, why do you use soap when you're washing things? Why do we use soap like when we're washing clothing or when we're washing our dishes? Why can't we just wash it with water?
Because soap
you have
is
the chemical
attracted to
mix
like
with
the stains and stuff.
So soap is attracted to the stains. Anybody else have a hypothesis?
Or the-
So,
Because it's got stuff in it.
Water,
that
like, clings to the clothes and stuff like that.
So what, okay.
No, I got it. The soap. No, yeah, the soap is attracted to the water, and the water and soap is attracted to the stain.
Okay, you're getting closer. So, okay.
soap is.
So if you have, say if we have a dirty rag, if we just have water, because water has a cohesion affinity to other water molecules, they clump. And when water tries to get through your fabric, sometimes it doesn't get through the fabric that well. Sometimes it doesn't get through and knock off the dirt. Guess what soap does to those water clumps? Breaks them down. Now the itty bitty water can get through the fabric and knock off all that dirt. Same with dishes. The soap breaks down the water inside your dishwasher, inside anything, so it can maneuver in and out of the food particles. So we use detergent or soap to break down these bonds between water so it can get really small and go in and out of your fabric or through your food. Isn't that cool? Okay, does everybody have the 3 water molecules and the bonds? Good. And remember, that was cohesion. Okay, this is a review from last year, but it's always good to review. So what we're going to do is we're going to talk about the 3 states of matter, which is solids, liquids, and gases, and we're going to talk about the motion, energy, shape, and give an example of each. So let's do a solid first. So if you're a solid, describe the molecules in a solid.
That's not like vibrating.
They're just vibrating. They're not even moving, okay? So the motion, no movement, just vibration. Now if you're not moving, you have stored energy. What kind of energy is that? Potential.
Yeah.
So you're just vibrating, you're not moving. You have potential energy. What is the shape? Do you have a defined shape if you're a solid? Yeah, you have a shape. And what's an example of a solid?
Square.
Yeah, your table. Okay? So when we're describing the motion, there's no movement, just vibrations. The particles are really close together. There's potential energy. It has a defined shape, and an example is a desk. Now what about liquids? Tell me about the motion of liquids.
They're like kind of moving.
Yeah, they're moving slowly.
And kind of spread out a little.
Spread out and moving slowly. What kind of energy?
50, 60,
Yeah, it has some potential and kinetic now. So good. You're moving slowly. The molecules are a little apart. You have some more kinetic energy now. What about the shape? Is there a defined shape of a liquid?
It can't, not really. It takes the shape of its container.
Takes the shape of its container. And then what is an example of a liquid? How about this?
Water.
Tell me, good. I was gonna say, what is the universal solvent?
Water.
Water, good.
Oh, I was gonna say that because it's the easiest
Yep. And then the gases. Tell me what the molecules in a gas.
one.
They're moving fast, they're spread out, there's a lot of what kind of energy?
Kinetic.
Kinetic energy. Does it have a shape?
No.
No. What's an example?
Gas.
What kind of gas?
Oxygen.
Oxygen, good. So make sure you have all of those 4 qualities written down. So for our solids, there's the molecules are close together, no motion, just vibrations. There's a lot of potential energy.
What?
No, make sure you have this written down. Our liquids, we have some motion. The molecules are a little spread out. There's some kinetic energy. Takes the shape of a container. Example is water. And then gas. The molecules are spread out. They're moving really fast. There's a lot of kinetic energy. There's no shape. And then we have oxygen.
Oh, that was the first thing. I apologize. Just start doing it here. I know.
Okay, who's still copying? Okay, so this is where we're going to start talking about our new terms, diffusion and osmosis. So, from the video yesterday, I don't know if you remember, but diffusion, think of the word to diffuse. Diffusion,
It spreads throughout.
good. So, write this down for your definition. The movement of particles. So, for your diffusion definition, movement of particles from high concentration to low concentration. Movement of particles from high concentration to low concentration. Yes, you can say diffusion is when particles spread out, but on your tax test, and the correct definition is when particles move from a high concentration to a low concentration. Can I have 2 volunteers?
Oh.
I see 1, 2.
Aw.
Okay, Carrie, show this side of the room, Marissa, show this side of the room. What I want you to do is I want you to drop 5 dye droplets in your water. So guys, when are the droplets going to be the most concentrated? So when are they most concentrated? Right when you drop them in. Look at how concentrated the dye is. What is it doing now? Diffusing, spreading out or diffusing. Good. Hey, what is a catalyst we can do to increase the diffusion? Stir it. So there's one stir rod, I have another stir rod. But guys, just look at how it's very concentrated.
Why do you think backwards?
That's how you smoke it.
Good. So look at, see how Marissa's is very concentrated toward where the dye just dropped in? Good, and now it's completely diffused.
Can't be. Like, fuck.
Like when you dye an egg.
Yeah.
Like for each day.
Also, another example is like if you're smoking a cigarette, and you should not do that. But if you do, you smoke, you blow out the smoke, it's first concentrated, it's first concentrated by your mouth, and then it diffuses across the room. Awesome, guys. Thank you.
Quick look at that new with your fingers.
Now you should leave it like that and you put some blue in it. Red and blue.
Mine looks good.
How about this? On a side note,
Run, yeah.
these water particle, water dye containers have the same density?
Yes.
Yeah, they're both water. So if I mix them, what's gonna happen? Are they gonna mix or are they gonna stay separate?
They're gonna mix.
They're gonna what? They're gonna mix?
And
Yeah, same densities, they're gonna mix. Okay, so write down the results of this dye experiment in your own words. So dye experiment, what happens? Tell me what happened in your own words. Try to use the vocabulary we just learned. Awesome. So what I tell you next is that all liquids act differently with other liquids depending on what they're made of. So if you mix two liquids together, they'll mix if they're similar, if they have similar densities. But if one is a lot more dense than another, like we learned last year, they're going to separate. So density, what is that, guys? If I say something is really dense, what are we talking about?
it's like more packed together.
Yeah, it's more packed, so it's the amount of particles per space. So
Kinda like
density.
Kind of like oil.
Yeah. So some things like oil are less dense than some things like corn syrup. So guys, for your definition of density, what is density? The amount of particles per volume. So if something has fewer particles per its volume, it's going to be less dense. If something has a lot of packed particles per volume, it's going to be more dense.
The amount of volume per density.
Amount of particles per volume.
Oh, yeah.
Because remember the formula, density equals mass divided by volume.
What type of liquids are we
So yeah, what type of liquids are dense? We did
Corn syrup.
corn syrup. Syrups are really dense. My Yankee accent coming out? Okay. How about this? Quentin, what happens when a dense, thick liquid is poured into a less dense solution? It mixes slowly. Who has another answer?
It goes down to the bottom.
It goes to the bottom. Let's try that out. Who didn't get to volunteer?
Me.
So why don't you mix,
Wait.
Is that corn syrup?
this is corn syrup. So why don't you hold that so everybody can see? And why don't you mix some water in there first? Put some water. Okay, we got some blue water first.
Uh-oh. Oh, man.
That's good. Now let's put some red water. What are the densities of these two? Are they similar or different?
They're similar.
Similar, so what should happen?
Mix.
Good.
I know.
Mix and turn purple, perfect. Now let's pour just a little of the corn syrup in and see how that reacts. Okay, that's good.
It went to the bottom.
The more attention goes to the bottom because it weighs more.
Good. So the dense goes to the bottom. I could probably separate these, so I could probably separate it out. And guys, if I mix this up really, really good, it would still separate. Awesome, thank you.
Good job. You're pretty.
So the answer to that question would be the denser liquid will go to the bottom, the less dense would stay at the top. Jermaine, next question. What happens when a low density water solution is poured into another low density water solution? So what happened when we put our low density blue water into our low density red water?
They mixed.
They mix. Good. So if you have two likes, you put them together and they will mix. So two things with the same density will mix. Okay, what I did before you guys came in here was I mixed.
Is that Kool-Aid?
Do you want to drink it? Do you want to try it? Want to see if it's Kool-Aid?
No.
Okay, what I did was I mixed some soap with some vinegar with some corn syrup, with some green water, and then I put in a wood chip, a penny, and a little plastic ball. Okay.
Oh, it's corn syrup at the bottom.
Yeah, let's look at the liquids first. Which liquid out of the soap, vinegar, corn syrup, and water do you think sank to the bottom? Which one was most dense? Corn syrup, awesome. Now I kind of have this like green globby mess. So this is a mix of water, vinegar, and soap. Now, you could kind of see that the soap is eventually falling to the bottom. At first when I put the soap in, it stuck to the top, and then it started being pulled down. So even though this is kind of soapy water, because the water is mixing a little with the soap is accumulated right here. So what can you say about the density of the soap compared to the water?
It's more dense.
It's more dense, good. And then you can kind of see at the top where it's the less cloudy, that's where the vinegar is, okay? Pennies all the way at the bottom, and then the wood chip and the plastic is at the top. I was trying to find something that would set at about right here, but I couldn't, okay? And if we shook it up really good, it would settle out to this also. Okay, now the next density question might not be as obvious. And so now we have to think about that definition. Number of particles per volume. If you had two pitchers, okay? Pitcher one had Kool-Aid in with just one packet of Kool-Aid. So you had a pitcher filled up to the top with water, and then you dumped one packet of Kool-Aid. Shook it up. That's Kool-Aid pitcher number one. Then you had another pitcher of Kool-Aid with 3 packets in. Which is more dense?
The second.
The second one. Why? It has more particles.
The more it is, the more dense it is.
Good. But if I increase the water that I added to it, it wouldn't. It would be equal. So if I said I had one pitcher and 1 packet, and then I put 3 pitchers and 3 packets, they're the same dense, okay? But because they're the same volume, but 1 packet's in this one and 3 packets are in this one is more dense. Okay, the earth and even your body are mostly made of water or liquids containing water. When things diffuse in and out of your body, they do not use energy, okay? If things diffuse, it means they do it without energy, okay? We are going to be learning about active transport where you can actively use energy, but most things that diffuse, they do diffuse without energy. Molecules that are diffusible go into and come out of cells freely. Other molecules require the energy for the transport in and out of the cell. Okay, so I just told you that certain molecules can diffuse in and out of a cell, but when we talk about osmosis, are we talking about particles moving? No, we're talking about what moving?
Water.
Water, good. So osmosis is the movement of water from low concentration to high concentration. Osmosis is the movement of water from low concentration to high concentration. And that's kind of opposite of diffusion. But what the water's doing is it's trying to dilute out the high concentrated area to get equilibrium. Because if you have 2 sides of, let's just say 2 containers of water, okay? This one has 1 packet of Kool-Aid, and this one has 3 packets of Kool-Aid, and you can't move the Kool-Aid particles. What would you have to do to get them to have the same concentration? So if you could move water instead of the Kool-Aid packet, right, you would have to move water into the highly concentrated area. Good. So there's 3 types of solutions. There's solutions where there's the same concentration inside as outside, And so there's equilibrium. There's the same concentration inside as outside. Then there's solutions where there's more outside than there is inside. So if there's only a couple particles inside and there's a lot of particles outside, where's the water going to go?
Outside.
Outside. Think of like it as people. Where do you want to go? You want to go where the party is. You want to go where more people are. You go outside. Okay, how about this one? You have a lot of particles inside and a little outside. Where's the water going to go? Inside. So I have that drawn for you up here. Okay,